probably a couple of ways.
Okay,
I just did it separately and added them at the end. You could have probably added them at the start.
so let's get started. Look, things to follow up on after the midterm. I was talking to many of you perhaps, Tuesday, just about a couple of things on the midterm and grading thereof. So the first thing has to do with the problem one. And I thought in a little bit of sense, so I haven't seen too much directly, that a few of you may have been, I'm not sure yet whether appropriately or inappropriately, because I haven't seen enough examples, but a few of you may have had two things happen on that first problem. The first being that an early error, numerical, propagating forward was penalized multiple times, which is not what the graders are advised and have to do. And then the second thing, which has to do with being maybe doctor point, if your answers, numerical answers in terms of significant figures, is very different than the information provided. So I'm waiting for feedback from the grader on that, just to understand the grader's perspective. Depending on what I learn, I will act or not act, but just hold on for a little while longer until I understand better what happened on problem one. On problem three, a number of you talked to me after Tuesday about an issue which turns out the grader was doing the right thing in this case. At the end of part A of problem 3, you might recall it was set up in a way that might seem a little, just kind of, it's a twist on it that a lot of you didn't catch. And so in fact that problem asks for you to give a generic expression for the electric field at some variable distance x in the way it's set up that is beyond that particular point, which is a distance a from the end of the charge distribution. So a lot of you correctly did the electric field calculation at that point, which is a distance a away from the end of the charge distribution, but did not just do that final step of translating it into an electric field, which is a variable distance beyond that point a. So I've seen a few examples that you presented to me after class of people using a couple of points there, and having looked at that carefully, that is appropriate if indeed you didn't go that extra step to give the expression for this generic point, the distance beyond the point A. So I wanted to make sure that was clear. Regrades, I'm still kind of a little bit hesitant about quite what to do here, because I still want to hear more from the grader of problem 1. Whatever input I get, I expect to get pretty quickly today. So at that point, I'll make a firm decision on what to do, if anything, about that problem 1. Roughly speaking, either way, whether I kind of ask all of you to hand them back in and have the person look at it again, or it's just the usual regrade submission procedure, that will run for the next week. So the sort of deadline for regrade requests or regrades of the first problem en masse will happen over the next week. A few of you have been asking about letter grades, and I've had discussions with some of you about that in office hours, so thank you for input on that. So many of you were in first semester, and you know there was a similarly, let me say, relatively high performance on the first semester. That's by design. So the question of letter grades, I'm always a little unsure what to do here, so I don't want to spend a lot of time on this, but I do want to reiterate the whole grading procedure, and then explain what I'm planning on doing in terms of letter grades with this first midterm. So let me remind you, the sort of overall performance assessment on the course has 5 components in principle: homeworks, recitation attendance, 2 midterm scores, final score. And then the sort of initial weighting scheme is described on courseworks, the weights associated to each of those things. what happens at the end of the course is that that initial weighting is done. There's a numerical score based on all of those components, and it's that final distribution that is, in a sense, curved, to use the common phrase, and which will give a distribution, and all of those components are folded in such that the median score, median grade, is sort of in the middle of the B+ range. Okay, that was the same for the first semester. Many of you have heard me say that throughout last semester. You've heard me say it a few times this semester, but until grades are issued, it doesn't actually, I think, really, it's only at that point that the sort of way that scheme works actually becomes apparent. And what do I mean by that? What I mean by that is, inevitably, you're going to kind of compare your letter grades for 3 exams, and then your tendency is going to be to look at homework and recitation attendance contribution, which would be, for most people, very high, and to imagine that therefore they fold in with, if you want to associate a letter grade with them, let's say an A or an A+ letter grade, all of which I remind you is based on the curve itself. For most of you, you're familiar with from high school, but again, it's just an arbitrary translation between numerical percentage score and the letter grade. So that has the effect, which many of you experienced at the end of the fall semester, that somehow your expectation is skewed by the contributions that you think come in with an A or an A+ contribution from homework and recitation. But again, let me remind you that the whole distribution is what I work with, and then that's what's curved in the way described. So I want to remind you of that because, and then there's also the parallel scheme where I drop your lower ranking midterm to sort of mitigate against any bad day you may have on one of the midterms, and the same procedure applies. So I want to remind you of that just because I want you to get away from kind of, and I know it's a natural thing to do, kind of looking at letter grades from 3 exams and then assuming that the high component from the recitation and homework kind of lifts that letter grade up. It does not. And that doesn't mean to say it's unimportant. It just means that most of you are lifted up by the same amount, and of course it's the final distribution that is curved. So you've heard me use the phrase, all roads raised equally several times. That's what I mean by that. So you might, again, that tends, I think, at the end of the semester to make you feel somehow thwarted, which is, of course, not what's happening. It's simply a reflection of the fact that recitation attendance and homeworks are vital for you to do well in the course. And so there are incentives to do them, of course, but most people get high scores on all of those things. So in a sense, that's kind of an integral part of the course. It's incentivizing you to do the necessary work to do well on the exams. So, with all of that said, I've been grappling with what to do with letter grades in this first midterm. My inclination is to be less specific about approximate letter grades associated with this. And again, I've spoken to some of you about this, not just in this course, but your experiences in other courses. Since it's such a high distribution, my intention, though perhaps not as high as, let me say, it's higher than I perhaps even bargained for. I strongly don't want you to feel that you are being graded or curved down. And I remind you what all of this means. Curved down for you, as far as I can tell, is a different curve than the one that you're used to from high school, which is itself just a curve. Okay, so these are all various types of correlations between percentage grades and letter grades. So in reality, I expect if I did do detailed letter distributions, it would probably look fairly close to a sort of high school translation that you're used to, in the sense that it probably would be true that 90% and above is some kind of A grade for this exam, 80% and above maybe some kind of B grade. As you know, I tend on the downside of the curve to curve up everything, and I feel that's appropriate. say that I don't feel I want to give very detailed letter grade guidance for this first midterm. I welcome your thoughts on this, maybe not in class right now because we want to get back into the class material. But I wanted you to understand why I'm doing this, explain how it worked last semester, and just, again, happy to talk to you about this in detail, but maybe not in class right now. So, I still haven't quite decided on that, but that's my current inclination. Related to that, as promised, it's a good time for you guys to tell me what's working and what's not. So this may factor into what you write on here. So I'm just going to distribute these as I did last semester. It's just a solicitation for feedback, things that are working and things that are not. So just grab one of these through the duration of class, and certainly by the end. Write on here anything that you feel is good, but more importantly, things that are not good, and things that would better help you to do well in the course, okay? They're anonymous, of course, no names on them, and I'm just going to ask you to hand them in after class, okay? So be candid. Most useful is things that you think could be changed that we can help for, okay? So keep that in mind. And then lastly, as promised, prospect of free lunch at that time of the semester. So after class, if you're interested, I have set 3 dates, lunch dates. They're up on the board on that side. There are associated sign-up sheets if you're interested across the front. And in case you can't make any of those, there's a sheet for interested but can't make any of those, okay? So if you're interested, sign up after class, and then we'll get back to you about free lunch. Okay, a lot of talking, more than I generally like to do on non-material stuff at the start of class, but any quick questions? Again, I'd rather not talk about the pros and cons of letter grades associated to the midterm right now, but I'm happy to talk about that offline. Other questions? Okay, good, thank you. So, just want to wrap up on a couple of things associated with charges and conductors, and electric fields and conductors. And then we're going to turn our attention for the rest of the day to energy basis of understanding electric charges. And I want to remind you a little bit of how this looked for gravitation. In principle, it's the exact same sort of sequence of approaches with a caveat. And what do I mean by that? If you remember our discussion of gravitation in the first semester, we start out basically just describing the gravitational force. And we're most used to starting that out with what we take as an approximation for near-Earth gravitation. Then we expand our consideration to, let's say, more general gravitation and Newtonian gravitation force law, which of course applies to any mass distributions. So we spend some time working on talking about forces, and then recognizing that gravitation is an example of a so-called conservative force. We then go on to talk about energy, in particular gravitational potential energy. Okay? So we're kind of going to be following the same tack with Coulomb force, again, another conservative force. So we introduced that early on in its most general form, so Coulomb's law. We have not really had cause to look at the very special case that is exactly analogous to near-Earth surface gravitation, where the gravitational force, and this is an area where we didn't draw parallels at the time, but now we can define little g as essentially a gravitational field produced by a mass distribution. Okay, we didn't talk too much about that in the first semester, but as you're about to see, it's exactly analogous. So we could describe little g as essentially being a gravitational field. And the near-Earth approximation, of course, if you think about it, is where that gravitational field is uniform. The analogous situation in electric fields is where we have a uniform electric field, and one way to produce that, you now know, might be to have a region between, let's say, infinite parallel planes, one that maybe carries positive charge. Whether we have another one carrying negative charge actually doesn't matter, because you know that the electric field, any distance away from an infinite plane of charge, is uniform, perpendicular to the field. So that's one mechanism we could use to look at the parallel between near-Earth uniform gravitational field and now a general uniform electric field. And then turning our attention to energy, of course, we talk quite a bit about gravitational potential energy. We're about to introduce the analogous electrical potential energy. And we're going to take that a little step further again than we did with gravitation. And I'm just going to be very brief in describing that so you know what's coming up this morning. Of course, the potential energy is dependent on two or more objects. Two or more masses if we're talking about gravitational potential energy, two or more charges if we're talking about electric potential energy. But it might be nice, as we saw when we defined the electric field from the originating Coulomb force, it might be nice to remove the effect of a second test object, whether it's in gravitation, test mass, or in electrostatics, test charge. And what that allows us to come up with is something which is what we describe as a potential. So we're going to be talking about an electric potential, and that's simply something related to the potential energy that it would endow to a system if I introduced a test charge into it. Okay? So that's going to be our roadmap for this morning, once we've wrapped up on electric fields and charges in conductors. So it's going to be an energy focus for the rest of today and into next week. And you'll hopefully see the advantages without the same weight, so the advantages of gravitation as we go along. So let me come back to the question of charges and conductors. So a couple of things I think I just want to talk about. So charges and fields, and there's going to be a little bit of talk about Gauss in here as well. So I want to come back to this sort of conceptual setup with a blob of conductor, random shaped blob of conductor. It's three-dimensional, okay, chunk of metal. What we learned about on Tuesday last time is, let's say we start off with this as being electrically neutral. Regardless of whether we're talking about a real metal or a sort of idealized conductor, we are assuming that both positive and negative charges within that material can move freely. Okay? But to begin with, it's electrically neutral. So everywhere we expect electrical neutrality in this chunk of conductor. So the question we asked and then answered on Tuesday is what happens if I put a bunch of additional charge? So I create a net charge of one type or another. And so, I don't know, maybe I put plus Q on this thing. And we learned through a couple of lines of reasoning on Tuesday that we expect this excess charge to be distributed around the outside. Okay? So, something like this, total plus Q. The question we started to address on Tuesday, which becomes sort of quite interesting, is what happens now if I carve out in the interior here, remember this is three-dimensional, so that cavity is fully enclosed by conductor. What happens if I put cavities inside the conductor? So we had a little bit of discussion about does some of that additional charge congregate on the inner surface? We concluded the answer is no. Okay? Basically using Gauss's law and the observation that the electric field in a conductor, if we have no currents flowing, no charges in motion, the electric field in the conductor is zero. Okay? So that's a kind of important consideration. So let me extend this, and I did this with a few of you in office hours between Tuesday and today, and complicate this situation by imagining that it's not just a cavity with nothing in it, but it's a cavity that I throw some charge inside. And let's see if we can figure out what happens here. So I'm going to reproduce exactly an example I did in office hour yesterday. And imagine that within that cavity, I'm now putting a charge plus little q. Okay? And the question is, what does the resulting charge distribution overall look like? And we could even address the question, what does the electric field look like? Also, we have time. First off, what do you expect now in terms of charge distribution within the conductor?
The electric field is so
Okay. I'm going to repeat what you said so everyone can sort of hear it. What you said is correct. The electric field in the bulk of this conductor is still 0. So I'm going to need to worry about two things, but the first thing I'm going to worry about is Gauss's law. And so in order for me to retain the requirement of the electric field in the bulk of the conductor is 0, I'm going to imagine a Gaussian surface that kind of wraps around the cavity and it's somewhere within the bulk of the conductor. And it should be true if the electric field everywhere here is 0, that there's no net enclosed charge, Gauss's law. The only way that can be true, I've got plus Q in the middle, it's not free to move, and I'm putting it there and it's staying there, so I can stick it in the middle here. The only way that can be true is if somehow around the inner surface that just wraps around the cavity, I have negative Q to cancel out the positive Q that I've stuck in the middle. And if you think about it, that green dashed line that was supposed to represent my Gaussian surface can go anywhere within the bulk of the conductor. So the only place that this negative Q can reside is literally right on the skin of that inner surface. Okay? So that's one requirement that comes from Gauss's law, and that the electric field within the bulk of the conductor is 0. But the second part of this, and this is what Secure was working for in office hour yesterday, is then to address the question, well, on the conductor itself, the net charge is plus big Q. So now I've got some minus little q on the interior surface. What does that tell you about the total charge on the outermost surface of the conductor now? Wouldn't that be little q? Does that allow me to, I found yesterday, not surprisingly, this is maybe a little bit easier to figure out if you actually put numerical examples in here. But does having little q on the outer surface constrain does it satisfy our charge conservation?
Big Q minus little q.
So I've got negative q here. Remember, before that appeared, after I put this in here, I had a total charge of plus q, but now I've got minus q here. This actually becomes big Q plus little q, right? Yeah.
Can you just quickly explain how we got to the conclusion that there's no electric field within a conductor?
So far, I'm just going to say it's by observation. We never see any currents inside situations like this. And the current, of course, is a moving charge. We're going to talk a lot about that in a couple of sessions from now. The only way I can have moving charges is if they're being driven by an electric field. We never see currents, persistent currents in situations like this. So we just don't observe it. So for now, that's the justification for saying that the electric field inside must be 0.
And then the same applies for an insulator, right? Or can you?
No, definitely doesn't apply for an insulator.
So you can have an electric field through an insulator, but not through a conductor.
In the bulk of correct, yes. Yeah. You don't necessarily have to have the electric field within the bulk of an insulator, but you certainly can. Whereas in the bulk of a conductor, in the absence of persistent currents, and you keep hearing me say this slightly cryptically, the reason is in a while in this course we're going to talk about cases where we do have electric fields that drive persistent currents in conductors, but for now we confine ourselves to situations where we don't observe such currents.
And then one more tiny thing. So in an insulator, I think this might just be a misunderstanding of how I understand insulators, but if charge can't flow in an insulator, how do you have a current or an electric field?
Okay, so they're two different things, right?
Okay.
So indeed, charges in perfect insulators, they're not moving, but there's nothing to prevent me, both conceptually and in real life, from embedding within an insulator charges however I want to. I can stick them in places and they're going to stay there. Now, if there are charges around, you naturally expect there are electric fields, for sure. And so there are always, if I've got, let's say, asymmetries and isolated charge distributions in insulators, they will be producing electric fields. But there's nothing that can move under the influence of those electric fields, right? So what we are talking about when charges move is that. And so this is only true if they're able to move, if they're conductors. But if they're fixed in place, these forces are there, but they're not forces that allow them to move. There are other forces that are keeping them fixed in place. So it's perfectly possible to have electric fields in insulators, but again, idealized insulators, any charges within them are not able to move by definition. So it's fine to have electric fields, but I can't have them make charges, free charges move.
So just the word, like, can you have a current in an insulator, yes or no?
No.
Okay, but like then we're using the reason, like, but then you're using the justification that there's no current inside conductors to say there's no electric field, which is sort of what gets.
Because they can move, right?
Okay.
So if they can move, then you will get currents in electric fields. They go hand in hand if they can move.
Okay.
So it's the observation in these situations that I never see currents.
Okay, that makes sense.
Yeah. Okay. So I know from experience that this type of confusion is quite prevalent early on, so it's good to talk about it. So Elizabeth.
Distribution of the plus and positive charge on the coverage side. Is the small q charge located on the inside of the outer shell and the large q is on the outer part of the outer shell, or is it all?
This is all on the outside.
It's all on the outside of the outer shell.
Correct.
Yep.
Yeah. Okay. So again, to maintain charge conservation, I put plus Q on this thing, so that's always got to be the total net charge on this. But now, as soon as I put plus Q in here, I have to compensate for that, maintaining zero electric field in the bulk by having minus Q spread around the interior surface. And if I've got minus Q here, I still need to have a total of plus Q. So when I add these together with this, I must come back to my total big Q. But all the stuff in red there is on the outer surface. Go ahead.
So, but so they're all propelled to like, because I know they're on the outer line, but
Yeah.
is the small cube like drawn, if you have like a metal sheet as the outside of it, would the smaller cube charge drawn like to the inside of the metal sheet to compensate for the negative charge inside, or would they all be on the outer part of the metal sheet? I think this is complicated because it's such a thin thing. But
So I'm not quite sure what you're asking, but what I want you to think of is that any excess charge is on an infinitesimally thin surface around a conductor, whether it's on the inside in this case or on the outside. It's in an infinitesimally thin layer at the surface. That's all. That's the only thing I can say about where it is. So it's always on an infinitesimally thin layer, regardless of how much there is or whether the surface is on the inside or outside. I don't quite think that addressed your question.
I think it's fine.
It's okay?
So, like, is it like we have a charge in the center that's like plus little q, but since it like kind of goes to like the outside, then the absence of that then becomes like minus q? Is that kind of how that works?
Well, the absence of that, we just have plus big Q on the outside again. So, right? So I started off with that.
Right.
Okay, and there's plus big Q on the outside. That's the only asymmetric bit of charge. Everything else is electrically neutral. Then I stick plus Q in here, and everything else happens instantly. That happens
So-
immediately as a corollary.
Like, I guess like what's confusing me is, so is the plus q at the center or is it at the edge? Like in real time?
This,
Yeah.
this is at
Where-
the outside edge.
Okay, so but like the value of, okay, so like there's a point charge in the center, right?
It doesn't really have to be a point charge.
It's just the value of q, the value of the charge is thrown in the center. I guess like
Right.
physically it's just like charge is
Yeah,
like,
I mean, That's okay, I can take some charge, I don't know, I can scrape it off one of these Van de Graaff generators and I can, though it's a bit hard to get in the middle of something that's completely contained. Maybe I can set it up in some way where I put it there to begin with and sandwich two halves together or something. But yeah, no, there's some charge, doesn't have to be a point, doesn't have to be in the center, but there's some